Next major integration technique is integration by parts. And so the thing that we should be thinking about if we have integration by parts is, can we split the integrand into two chunks, u and dv, such that u is easy to take the derivative of and v is easy to integrate, because in that case we know we can rewrite it as uv minus the integral of v du. The important thing there is that you have to come up with u and dv such that their product is the entirety of what's here. So if you're looking at various products, that's something that should be popping into your mind. If you see something times something, think about integration by parts. There's several special cases to think about, other than just the most obvious case. About the first thing that you do here is something like x e to the x dx. And so this very obviously has u is x, du is dx, dv is equal to e to the x dx, and v is equal to e to the x. So note here I have u dv is this entire thing here, so that's good. And what happens here? This is uv x e to the x minus the integral of v du. V du, e to the x dx. And that's much easier to integrate. Let's look at some special cases. So special case number one is that sometimes you have something of the form x to the n times some function. And so if that function f of x is something that's easy to integrate, sometimes it's a good idea to set, so if f of x is easily integrated, what you can do is set u to be x to the n, du is equal to n, x to the n minus 1 dx, and then you'll probably end up with something, if it's easily integrated, repeatedly integrated, you just kind of reduce the power of x time after time after time. So like if this is like sines, cosines, e to the x, some other trig functions, these are all good things to think about. Let me just show an example that I've written out here. If you're trying to integrate x squared cosine x dx, a good choice is u is x squared, du is 2x dx, dv is cosine x dx, so that gives v is sine x. Because when we write this out, take a look, we've reduced the thing that we're integrating from x squared times a trig function to just x times a trig function. We've made progress by going from x squared to x. And then if we do this one more time, u is x, du is dx, dv is sine x dx, v is minus cosine x. Look, we end up with the leftover integral is just cosine x. So we go from x to the 2 to x to the 1 to x to the 0, and now that's something that we can integrate. So watch out for this kind of just, you have a polynomial and the degree of the polynomial keeps going down. If I made this, instead of x squared, if I made this x to the 5th, it would be just as hard as what's going on here. It would just take more steps. You go x to the 5th to x to the 4th to x to the cubed to x squared to x to the 1 to x to the 0, and then you integrate at the end. So not any more difficult, just more tedious, for these higher powers of x's. So that's one special case. A second special case is, remember about the, I call it like the wraparound or the looping trick here. So we have the integral of e to the x cosine x dx, call that I. If we integrate once, we get e to the x sine x. If we integrate by parts again here, we end up with minus I over here, and then we take minus I, move it to the other side to get 2I, and then we end up dividing everything by 2. So watch out for these kinds of tricks where you loop around and then you're able to algebraically solve for the thing that you're integrating. It feels kind of magical because in some sense it feels like we're never actually integrating I, but we loop around, we get some equation involving I, we can solve for it. Okay, so that's our second special case to think about. A third special case is sometimes the way to think of our product is u is the entirety of this function f of x, and dv is just dx. So in that case, v would equal x. This comes up in a couple of special cases, in particular when you're dealing with something with logs or with inverse trig functions. So two examples of this. So this trick is good for logs and inverse trig. So for a log of x dx, if we try u is equal to natural log of x, dv is equal to dx, we get v is equal to x, and du is 1 over x dx. And so this is now just uv, x log x, minus the integral of v du. And so that's just integrating 1, so that's the antiderivative of 1 would be x plus a constant, which is easily checkable. So that's an example of logs, an example of inverse trig. So arctangent x, and we set u is equal to arctangent of x, and dv is equal to dx. V would be x, and the derivative of arctangent is 1 over 1 plus x squared. And so this is uv, x times arctangent, minus the integral of v, x, over times du. And that's very easy to do by substitution. U is equal to 1 plus x squared, du be 2x dx, and so that's how you attack this problem. Okay, so that's a third trick to think about in integration by parts. One final trick to think about is we usually are most comfortable choosing, if we see a power of x here, to choose that to be u. If I go back a couple of slides, that's like what we were doing here, choosing our power x to be u. Sometimes we want to choose the power x to be part of dv, and so we integrate instead of differentiate. So once again, here we have natural log. Natural logs and inverse trig functions, those really demand to be u. And so if we see a natural log here, it kind of cuts in line, it gets to be u, and so x squared is relegated to being part of dv. And so we calculate this out. U is natural log x, dv is x squared dx, so u times dv is equal to x squared log x dx. And so we write down this line, and that integral is easy for us to do. Okay, so that's a quick overview, a quick summary of integration by parts.